All right, so I don't know what happened. That was really weird. I came back and my computer was just whatever. So we're just gonna start this from the beginning so that everyone's on the same page, because then that video was no good anyways. Okay, so the Graham-Schmidt process is a simple algorithm for producing an orthogonal or orthonormal basis for any non-zero subspace of Rn. Okay, so the general idea is that you take a vector, so you have two vectors, and they're linearly independent. So therefore, they span this two-dimensional space, a plane, if it's in R3. What you do is you take the first vector, and then you project the second vector onto the first vector, or onto the span of the first vector. Then what you do is you take the difference between the second vector and the projected point, and you get something that's orthogonal to the first vector and has the same span. Anyways, if you iterate that process, then you get what's called the Graham-Schmidt process, where you just keep projecting onto the last subspace that you had. And you can prove it, and then then this section shows you how to normalize, and you just divide each vector by its norm. And okay, then they go into QR factorization. So we actually did spend a little bit of time on QR factorization. I thought that part was okay, but the speed run explanation of what QR factorization is that if you have some linearly independent m by n matrix A, you can factor it into QR, where Q is an orthonormal basis for the column space of A, and R is an invertible n by n upper triangular matrix with positive entries on its diagonal. It's upper triangular. Oh yeah, it's upper triangular. You should be able to see that it's upper triangular, because the point is that one of the key conditions of the normalization process is that it's iterative. So we continually add to our subspace W, and so that means that any of the first K elements of our original basis is the same for our orthonormal process. So the reason why that makes sense is that when we figure out what the linear combination is to form our original basis, it's only going to use the first K coefficients or first K basis elements. So that's why it's upper triangular. And it's positive. You can make it positive. You can make it positive if RKK is less than 0, multiply both RKK and UK by -1. But why do you want it to be, why do we want R to have positive entries on the diagonal? Okay, so what I was trying to understand is, so let me just open up this. This shouldn't be the golf project, right? This should be, okay, yeah, so let's open up. All right, so that's the whole section. That's actually really easy. When Gram-Schmidt processes run on a computer, round-off error can build up as the vectors u, k are calculated one by one. For j and k large but unequal, uj transpose uk So what's the point of QR factorization, though? Oh, okay. So the point is to... The point is for least squares. So they haven't really got into that yet. This loss of orthogonality can be reduced substantially by rearranging the order of calculations. Huh. However, a different computer-based QR factorization is usually preferred to this modified Gram-Schmidt method because it produces a more... So how do they actually do QR factorization? Okay. Uh, to produce a QR factorization of matrix A computer program usually left multiplies A by a sequence of orthogonal matrices until A is transformed into an upper triangular matrix. This is analogous to elementary matrix multiplication for LU factorization. I always forget. That's right. That makes sense, sort of. I need to work through examples. Okay, so let's read the problems, but I think I'm only going to do true falses probably. Okay, so what you do is you just take the projection of this onto this vector, and then you subtract the projection from this, and you get the difference, and then that's your new. Then that's your orthogonal basis. For find an orthonormal, you just do the same thing. Find an orthogonal basis for the column space of each matrix. Alright, in exercise 13 and 14, the columns of Q were obtained by applying the Graham-Schmidt process to the columns of A. Find an upper triangular matrix R such that A equals QR. Alright, let's just do these. Alright, 17. In general, I would say no, it's not a new basis. It's not a new basis because it's like, it's the same basis, man. I mean, it's not the exact same basis, but it's the same basis. If W... What's the definition of orthogonal set? So, this is false because we don't know what the... Oh, wait. Oh, I now know what this means. This is true. That's true. Gram-Schmidt process produces... The Gram-Schmidt process produces from a linearly independent set an orthogonal set with the property that for each k... the vectors span the same subspace. That is true. That's true. That's exactly what Gram-Schmidt does. If X is not in a subspace W, then X minus the projection onto W of X is not 0. That's true. If A equals QR, where R has orthonormal columns, then R is equal to Q transform A. If we have A is equal to QR. Now I forget, if something has ortho... So if we left multiply A equals QR by Q transpose, then we get Q transpose A is equal to Q transpose QR, which is equal to the identity, because it has orthonormal columns. Right, if it's not... Yeah, if they're orthogonal, then all the non-equal ones are 0. And if they're equal, then they have norm 1, which means that the square of 1 is 1. Okay, so this one is true. In a QR factorization, say A equals QR, where A is linearly independent columns, then the columns of Q form an orthonormal basis for the column space of A. Yes. So that's true. 23. Okay, wait. That's all. So let's just double check if we got these right. I think all of those make sense, right? All right. False, true, 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 and that's it. All right, so we did get them all right. That was easy. Why must R be invertible? It's a good question. So let's just think about what are the columns of A. If in 23, if A equals QR, I don't think this gives us that they're orthonormal. So we just have to so we have Q1 to Qn of length M, and then we have uh, let U1 to UP be an orthogonal basis for subspace W, and let show that T is a linear transformation. All right, this one's easy. We don't need to do this one. What this one amounts to is you take ax plus b. You take ax plus by and you feed it in here, and you show that you're able to separate them out into two separate linear combinations. So, i.e., two separate projections. So then you show that, t of ax plus by is equal to a times proj under w of x plus b times proj under w of y, and therefore t is a linear transformation. Suppose A equals QR is a QR factorization of an m by n matrix A with linearly independent columns. Partition A, where A1 is P columns, show how to obtain a QR factorization of Okay, so I don't know the answer to this, but it depends on the fact that the Gram-Schmidt QR factorization forms something where the first k columns of A have the same span as the first k columns of Q. That's what it all is about. I do want to look up the answer to this one though. Bro, but I am so tired, man. I did not sleep well. All right. So wait, before we just cheat, let's just think about what the heck we're trying to prove. Suppose A is equal to QR. Show that if A is linearly independent columns, then R has to be invertible. All right, we can stop being dumb. So if A is equal to A1 to AN as columns, and then we have Q R So what is R? That's the thing is, are we assuming that R is this upper triangular thing? Or are we just saying R is some? Okay. Oh yeah, that's easy. Oh, I should have been able to figure that out. Consider for contradiction that exists x not equal to 0 such that r times x is equal to 0, then qrx is equal to 0 implies that ax equal to 0, right? But then that's a contradiction because a is linearly independent. So that's all you have to do. All right, then this one, we're trying to now show that r is invertible. So we assume r is invertible, and we want to say that A and Q have the same column space. And the hint is, given Y in the column space of A, show that Y equal to QX for some X, and then given Y and call Q. Yeah, so you do like a double inclusion thing. Right, given y and call a. So we say that ax, so this is 24, so we say ax is equal to y. Now we want to know that then we want to show there exists an x prime such that q x prime is equal to y. Oh, since Rx is just another vector in Rn, we see y is a linear combination. Yeah, okay. Yeah, since Rx is in Rn, then Q times Rx is equal to y. So we just let Rx equal to x prime, and we're good. Now this one depends on the invertibility. So we say Ax, we take y in column space of Q, and y is equal to QU. Wait, hold on, let me do this. So now the reverse inclusion, we say y is equal to Q times U. Then we say U is equal to R times X, but then we just do R inverse of U. Wait. Since R is invertible, X is equal to, right. Oh, so then X, so then Q times R times X is equal to AX. Okay, cool. And that doesn't even rely on the orthonormality or anything like that. That's just what it is. All right, so this is actually a short section. I kind of like that it was a short section because I am beat. I'm so tired. All right, so we're gonna try to do the review chapter, but I need to take a nap or something, bro. I'm so tired.